Okay, so these equations are not proportions, so they're not fractions equal to fractions. So we're going to use Fraction Buster, which means we're going to multiply all of the terms, each and every one of them, by the denominator over 1, because the goal is to eliminate the denominator. So my LCD for number 66 is going to be 8x, because the common multiple of 2, 4, and 8 is 8, and then there's 1x there. So I'm going to multiply by 8x. And what happens is my x cancels, my 4 cancels the 8, and I get 2 times x plus 2. Minus, the 2 cancels the 8, x's cancel, and I get 4. And that's 3 times 4. And the 8 cancels, and I get equals x. So now we have 2x plus 4 minus 12 equals x. And we have a nice linear equation to solve. So I'm going to subtract my 2x. And I get negative 8 equals negative x. So x equals 8. 8 is not going to make the denominator 0, so it's not extraneous. Number 67, my LCD is going to be g plus 1 times g plus 9. Now, I'm going to write that down here so we can have space for it all. G over g plus 1 times g plus 1 times g plus 9 plus g over g plus 9, times g plus 1 over g plus 9 equals 1, and I have to multiply that side too, g plus 1, g plus 9. So my g plus 1 divides out, on my g plus 9 divides out, and I end up with g times g plus 9, which is g squared plus 9g, and I get plus g times g plus 1, and that's plus g squared plus g, equals g plus 1 times g plus 9, and that equals g squared plus 10g plus 9. So we're going to combine everything up. We have 10g on this side, so we have 2g squared plus 10g equals g squared plus 10g plus 9. And we subtract our 10g and subtract our g squared. Move everything up so we have some space. And that's g squared, the 10g's cancel, equals 9, and g equals plus or minus 3 when I take the square root of both sides. And neither of those will make this denominator in my original equation 0, so answer is plus or minus 3. And then lastly, on this page number 68, we're going to do the same thing. We're going to multiply by e plus 3, e minus 3. That's our LCD. E plus 3, e minus 3. Again, the goal is to eliminate the fraction, not get common denominators here. So 68, e over e plus 3 times e plus 3, e minus 3, plus 3 over e minus 3 times e plus 3, e minus 3, equals 4e plus 5 over e plus 3, e minus 3, times e plus 3, e minus 3. And what I get is the e plus 3 cancels, the e minus 3 cancels, and the whole denominator cancels on the other equal sign. So we get e times e minus 3, so e squared minus 3e. And we get 3 times e plus 3, so plus 3e plus 3. Nope, sorry, 9. Forget that distributing. Equals 4e plus 5. And so we combine like terms, we get e squared plus 9 equals 4e plus 5 minus the 4e and minus the 5. So we get e squared minus 4e plus 4 equals 0. And that's e minus 2 equals 0, so e equals 2. And that doesn't make the denominator 0 because the denominators are e plus 3 and e minus 3. And so my answer is just 2. A little bit of chapter 11 in here, or chapter 8, I guess, this book. Write a rule for the nth term of the arithmetic sequence. That's the an equals a1 plus n minus 1 times d. So my a1 is 35. When I write my rule, I leave n and I leave an, and all I need to find is my common difference. What am I adding every time? So 41 minus 35 is positive 6, so d is 6. And then I distribute 35 plus 6n minus 6. So 29 plus 6n equals your an, and that's your rule. Find the sum of the first 12 terms of the arithmetic sequence. And that is your Sn equals n over 2, a1 plus an formula. But I don't know an, so I have to find a12 using the first formula we used up here. A1 is negative 7 plus 12 minus 1, because I want the 12th term, so I'm plugging in 12 for d. That 12 came from here. My common difference is 8, so times 8. So negative 7 plus 11 times 8 is 88. And 81 is my a12. Now I can use my sum formula. The sum of the 12 terms is 12 over 2 times a1, which is 7, plus an, which is 81. 81 minus 7, 81 minus 7, 74. So 6 times 74 is 444. So that's our answer for number 70. Number 71, give the first 4 terms of the geometric sequence for which a1 is negative 2 and r is 3. That means we're going to multiply by 3. So a1 is negative 2. Multiplying by 3 gives us negative 6. Multiplying by 3 gives us negative 18. Multiplied by 3 gives us negative 54. And that's our first 4 terms. Number 72, find the sum. The summation means find the sum from 1 to 5 of 1/2 to the j. So to find a 1, I'm going to plug in 1. So 1/2 to the 1 is 1/2. If I'd like, I can plug in 5 to find an, or I can use my formula. This one, let's move this over a little bit. The S of n equals a1 times 1 minus r to the n power over 1 minus r. So all I need for that is a1, r, and n. So that's 1/2 times 1 minus r is 1/2 to the 5th power from 1 to 5 is 5 terms over 1 minus 1/2. So 1/2 times 1 minus 1/2 to the 5th over 1/2. The 1/2s cancel. And this is 1/2 to the 5th, so 1 minus 1 over 32, which is 31 over 32. And 73, find the sum of the infinite geometric series. Infinite is S equals a1 over 1 minus r, but r has to be between -1 and 1. So if r is greater than 1, the absolute value of 1, then it's no sum. But r is -1/3, so we're good. The absolute value is less than 1. So a1, let's plug it in. This is in our a1 r to the n minus 1 formula. but it doesn't hurt to just always plug in 1. So we get -3 times -1/3 to the 0, which is -3. So that's my first term over 1 minus -1/3, which is -3 over adding 4/3 and multiply by the reciprocal. So that's -3 times 3/4, which is -9/4. Make sure you do that part right. Find the sum of the geometric series. My A, this is ... means it's infinite. A1 in this case is 35, and R is 21, -21 divided by 35, which reduces to, I can divide those both by 7, -3/5. And so again, the formula is A1, 35, over 1 minus R, -3/5. So that's 35 divided by 1 plus 3/5 is 5/5 plus 3/5, which is 8/5. Multiplied by the reciprocal, so 35 times 5 over 8. And 35 times 5 is 175 over 8. Number 5, solve the given system. Now I have 5a plus 2c equals 4. I have -2a equals 20. Oh, this means I can find out what a equals. A equals -10. And if a equals -10, I can plug that into 5 times -10 plus 2c equals 4. -50 plus 2c equals 4. So 2c equals 54. So c equals 27. And then I can plug that in. 3b plus 12 times 27 equals 18. 12 times 27 is 324 minus 324 is 306. So 3b equals 306. So b equals 102. So my ordered triple is -10, 102, always alphabetical, and 27. And number 76, factor the polynomial completely. When I have 4 terms, that's factored by grouping. So I'm going to do 34xy minus 51y plus, and I'm going to bring the negative inside, 40x plus 60. I'm going to factor out a 17, 17y, and I get 2x minus 3. And I'm going to factor out a -20, and I get 2x minus 3. Now I can factor out my 2x minus 3. So 2x minus 3 times, if I take these out, taking those out, what's left is 17y minus 20. So 17y minus 20. And that's your factor. Number 77. Solve the equation. I have 2 powers of 10. So I'm going to write this 10 to the 7n minus 11 equals 10 to the -4 power, because 1 over 10,000 is 10 to the -4 power. That is 7n minus 11 equals -4. Add 11. 7n equals 7. So n equals 1. And Solve log base 32 of n equals 1/5. This I can rewrite 32 to the 1/5 power equals n. Rewrite it as an exponent, and n equals 2 because the 5th root of 32 is 2. Use the log 4 of 3 is about this, and the log 4 of 4 is 1 to approximate this. There's a problem, this crazy problem on the test, and let's divide this by 4. 384 divided by 4 is 96. So 96 times 4. And 96 divided by 4 is 24 times 4 times 4. And 24 is 4 times, or 8 times 3. So we have 8 times 3 times 4 times 4, and 8 is 2 times 4. So I get the log base 4 of 2 plus the log base 4 of 4, 1, 2, 3, 4 cubed, plus the log base 4 of 3. The log base 4 of 2 is 1/2, plus 1, plus 3. The log 4 of 4 cubed is 3, plus 0.7925. And I can add that all up. So 3.5 plus 0.7925 is 4.2925, which is kind of crazy because in this case, because you have a calculator and this is a really big number and it's going to take some time, I would just do the log of 384, the log of 384 in your calculator divided by the log of 4. And we get 4.292. So we could do all this work, or you could do it the short way. We're not checking your work, so that's a quick way to do that problem. Number 80 says the log base 2 of 3 plus the log base 2 of a equals log base 2 of 18. I don't know why those 2's are really big, but our product property says those can come together as the log base 2 of 3a equals the log base 2 of 18. And now our one-to-one property says that 3a has to equal 18 because my logs are the same. So 3a equals 18 and a equals 6. That one's nice and easy. Number 81. 9 to the 9x equals 19. So I'm going to rewrite this as the log base 9 of 19 equals 9x. Actually, no, just for consistency's sake, I want to write it as 9x equals the log base 9 of 19. And then I just want to do that part in my calculator. We can divide by 9. X equals the log base 9 of 19 over 9, which is approximately, remember that on SATs, you might have to just write it in this form, this exact form. So I'm going to do log 19, close the parentheses, divided by the log of 9, close the parentheses, I get 1.34 divided by 9, which is approximately 0.1489. And lastly, 82 here says e to the ln of 4, and e and ln are inverses, so that is just equal to 4. So we're going to solve these two equations. 7e to the x minus 7 equals 6. We're going to get the e to the x by itself before we can do anything. 7e to the x equals 13. e to the x equals 13/7. And I can rewrite this as a log. Log base e is a natural log. Natural log of 13/7 equals x. And we'll use the ln button, and in the parentheses do 13 divided by 7, close the parentheses. X is 0.619. It's 83, 84, 10,000th place, so that would be, well, it's actually a 0, so 0.619. 7 plus 2e to the 8x equals 22. Again, I need to isolate the e to the x term, so minus the 7. 2e to the 8x equals 15. Divide by 2. E to the 8x equals 15/2. Rewrite it as a log, so the natural log of 15/2. 8x equals the natural log of 15/2. And then we get divide by 8. So this would be the exact answer, the natural log of 15/2 divided by 8. Or x equals natural log of 15 divided by 2 is 2.0149 divided by 8 is 0.251